The Atlantic conveyor moves 50 times more energy than all of human civilization, and it is the only reason Northern Europe is not frozen like Siberia. New data just confirmed it has entered the first stage of a collapse. For 20 years, scientists could tell you this current was weakening, but not how close it was to stopping. A team in the Netherlands just built the tool that answers that question, and the first reading is alarming. Here's exactly what they found, and what it means for the years ahead. A team at Utrecht University in the Netherlands has just confirmed that the Atlantic Ocean is in the first stage of a collapse. Not at risk of entering it, not projected to enter it by the end of the century. Already inside it, right now, measurable in data we have been collecting for 30 years. The researchers ran the highest resolution simulation of the Atlantic conveyor ever attempted, and then they went looking for its fingerprint in the real ocean. They found it. The Gulf Stream has already drifted about 53 kilometers to the north since 1993, and that drift is the exact signature their model predicts for the opening stage of a collapse. Here is why this is a genuine turning point. For decades, scientists could tell you one thing about the Atlantic conveyor and not the other. They could tell you it was weakening. They could not tell you how close it was to stopping. Those are completely different questions. Measuring how fast a current is moving is not the same as measuring how close it is to failure. For 20 years, the field had what amounts to a speedometer, and what it needed was a fuel gauge. The Utrecht study just built the fuel gauge, and the first reading is that the tank is already draining. This matters to far more than oceanographers, because this is the current that keeps Northern Europe out of the Ice Age. By every rule of latitude, Britain and Scandinavia should be frozen. They are not, and the only reason is the river of tropical heat this conveyor delivers. So when the instrument that measures its collapse finally exists, and its first reading is stage 1, that is news everyone should hear. And it gets more specific from here. The reason this study could see what every study before it missed comes down to one word: resolution. The Utrecht team built a global simulation of the ocean at a resolution of about 10 kilometers. The standard climate models the field has relied on for decades work at about 100 kilometers. That is 10 times coarser. And that difference is the entire story, because at 100 kilometers, the Gulf Stream is a smear, and the deep current that controls its fate is invisible. Building a model that detailed takes extraordinary computing power. The team ran it on Snellius, the Dutch national supercomputer, a machine that performs roughly 14 quadrillion calculations every second. The simulation required about 6 months of continuous runtime. To put that in perspective, the same calculation on an ordinary laptop would take approximately 14 million years. That is the gap between a normal computer and the machine it took to resolve this collapse mechanism. 14 million years ago, modern humans did not exist. If you had started this one simulation on a laptop back then and let it run continuously through the entire evolution of our species, it would still be running today, nowhere near finished. That is the price of looking at the ocean clearly enough to see this collapse coming. The reason that resolution costs so much is that detail explodes the math. Every time you shrink the grid boxes, you multiply the number of boxes and the calculations connecting them. Going from 100 kilometers down to 10 kilometers is not 10 times the work. It is the kind of leap that moves a problem from something a university group can run to something that requires a nation's flagship supercomputer running flat out for half a year. And that expense is exactly why this mechanism stayed hidden for so long. The instrument that could finally read the conveyor's distance to collapse was buried in a level of detail the field had never been able to afford. What the team did with that digital ocean was push on it. They forced the model with a slowly increasing flow of fresh water into the North Atlantic, a controlled stand-in for the meltwater pouring off the Greenland ice sheet into the exact region where the conveyor sinks. Then they watched how the Gulf Stream responded, at a resolution fine enough to see not just that the system weakens, which everyone already knew, but how it actually breaks. And what it produced was a collapse pattern no model had ever captured before. The pattern the model produced has 2 stages, and the shape of those 2 stages is the most important result in the entire study. In the first stage, as the fresh water builds up, the Gulf Stream drifts gradually northward. Over roughly 400 simulated years, it creeps about 133 kilometers north. That is slow. It is the kind of signal you would never notice unless you knew exactly what to look for. And that slow, quiet drift is precisely what stage 1 looks like. Then stage 2 arrives, and stage 2 does not take 400 years. It takes about 2. In roughly 2 simulated years, the Gulf Stream lurches another 219 kilometers north, near a point on the American coast called Cape Hatteras, and the entire Atlantic conveyor breaks. Put those 2 numbers side by side, because the danger lives in the space between them. 400 years of slow drift, then 2 years of total collapse. The system holds for 4 centuries, giving off a signal so faint it is almost invisible, and then it fails in the span of time it takes to finish second grade. That asymmetry is why scientists use the language of tipping points, and why it is so alarming. A tipping point is not a gentle slope you can see coming and plan around. It is a ledge. The system holds steady, giving that slow, benign signal, and then it goes over all at once. There's one thin piece of warning built into the model, though. The stage 2 lurch arrives a few decades before the full collapse completes, which means the lurch itself is a precursor, something you could see coming if you were watching the Gulf Stream's position closely. And that raises the obvious question the team asked next. What actually makes the Gulf Stream lurch? The answer is a part of the system almost no one ever talks about. Everyone knows the Gulf Stream, the warm surface river off the American coast. But the Gulf Stream is only the top layer of something larger, and the part that controls its fate runs along the bottom of the ocean, in the cold and the dark. It is called the Deep Western Boundary Current, and it is the cold, dense return flow that carries chilled water from the North Atlantic back south along the seafloor. Here is what that deep current does. As it flows south, it passes directly beneath the point where the Gulf Stream separates from the American coast near Cape Hatteras. And at that spot, it generates a rotational force that pins the Gulf Stream in place. As long as the deep current is strong, that force holds the surface current anchored where it has always been. This is the mechanism the Utrecht team identified, and it is the key to the whole collapse. As the conveyor weakens, the deep current weakens with it. As the deep current weakens, the pinning force loosens. The point where the Gulf Stream lets go of the coast starts migrating north. That is what the 53-kilometer drift actually is. And when the deep current weakens past a critical point, the pinning fails completely, the Gulf Stream lurches, and the conveyor breaks. This mechanism had been described in pieces in older oceanographic literature, but no climate model had ever captured it. And now you know why. At 100 kilometers of resolution, the deep current does not exist in the simulation, and the Gulf Stream is too blurry to place. The pinning interaction simply cannot happen. The 10-kilometer grid was the first one fine enough to hold both the surface current and the deep current at once. And the moment both existed in the same model, the mechanism appeared, and the two-stage collapse wrote itself. It is worth being precise about what the drift physically is, because it makes the warning concrete. For most of its run up the American coast, the Gulf Stream hugs the shoreline. At Cape Hatteras, it separates and heads out into the open Atlantic toward Europe. That separation point is not fixed. It is held in place by the deep current beneath it. As the pinning loosens, the separation point migrates north, and the whole current reaches farther up the coast before turning out to sea. So, the 53 kilometers we are talking about is the place where the Gulf Stream lets go of America, creeping northward, exactly as a loosening grip would predict. That is not an abstract statistic. It is the physical signature of the conveyor weakening, measured in the position of the most famous current on Earth. Once the team had the fingerprint in the model, they went looking for it in the real ocean, and they had two completely independent places to look. The first was satellite altimetry. For more than 30 years, the Topex/Poseidon and Jason satellites have measured the height of the sea surface from orbit, and the shape of that surface reveals where the Gulf Stream sits. The team pulled a continuous 31-year record from 1993 through 2024. The second source was completely separate: subsurface temperature measurements from instruments in the water itself, with records reaching back to 1965. Both sources said exactly the same thing. The Gulf Stream has drifted approximately 53 kilometers north since 1993, a statistically significant shift in each record, processed independently. This is the number that matters. And notice where it comes from. It does not come from the model. It comes from the real ocean, confirmed two separate ways. That independent confirmation is what makes it so hard to dismiss. The satellite method and the temperature method share no equipment and no physical principle, so there is no single error that could fake the same drift in both. When two unrelated witnesses describe the same event the same way, it stops being a coincidence and starts being a fact. And here's the part that should genuinely unsettle you. That 53-kilometer signal was not new. The satellites had been recording it continuously since the early 1990s. The data sat in public archives for 3 decades. What changed in 2026 is that the Utrecht model finally identified the mechanism that made the drift legible as a stage 1 warning. Until the mechanism was named, the drift was a curiosity. Once it was named, it was an obvious alarm that had been sitting in plain sight the entire time, which raises the question everyone is now asking: how far into stage 1 are we? This is where the honesty has to be sharp, because the answer is genuinely uncertain. Stage 1, in the model, lasts roughly 400 years. The real Atlantic has been drifting for at least the 31 years the satellites have watched, and possibly decades longer, with no record fine enough to know when it began. So the 53-kilometer figure confirms we are inside stage 1. It does not tell us whether we are at the beginning, the middle, or near the end. That uncertainty is exactly why the comforting phrase people reach for, that the system is still reading within normal historical bounds, is not actually comforting. Remember the shape of the collapse. Stage 1 is the calm phase, the part where everything still looks normal and the drift is slow. The whole danger of a two-stage collapse is that the safe-looking phase and the about-to-fail phase look nearly identical from the inside. You are within normal bounds, right up until the 2 years when you are not. Being within bounds is not evidence that you are far from the edge. So what would actually tell us we are getting close? The drift rate. Not the drift itself, which we have, but the speed of it. Stage 1 is slow, steady drift. Stage 2 begins when the deep current loses its grip, and that transition shows up as an acceleration. If the Gulf Stream starts drifting north faster, that is the first observable sign that the system is crossing towards stage 2. And the breakthrough here is that we can now watch for exactly that, in near real time, using the same satellites that have measured the ocean for 30 years. For the first time, the conveyor has a gauge we can read, and we can watch whether the needle starts to fall faster. But to understand why that needle matters so much, you have to understand what this current actually does. The Atlantic conveyor moves about 1 petawatt of heat northward through the Atlantic. That number is almost impossible to feel, so here's the comparison. 1 petawatt is roughly 50 times the total energy consumption of all of human civilization, every second continuously. The conveyor begins in the Gulf of Mexico, where warm tropical water near 27 degrees Celsius is driven north along the United States east coast as the Gulf Stream, carrying about 80 million cubic meters of water every second in a current roughly 150 kilometers wide. As that water travels north, it releases its heat into the air, and that heat is the reason Northern Europe is livable. This is not a figure of speech. Britain sits at the same latitude as Siberia. Norway lines up with the southern tip of Greenland. Without the conveyor delivering tropical heat, average European winter temperatures would fall by about 10 degrees Celsius, London would face winter lows near minus 20, and Scandinavia would become tundra, colder than modern Siberia. The 53-kilometer drift the new study confirmed is happening to this machine, the one that keeps an entire continent from freezing. So what threatens it? Fresh water. The whole conveyor runs on density. Cold water is denser than warm, and salty water is denser than fresh. The sinking that drives the entire circulation depends on a precise density contrast in the North Atlantic. As Greenland melts, cold, fresh meltwater pours into that exact sinking region, dilutes the salinity, and weakens the density contrast. The water still tries to sink, but with less force, and the whole system loses energy. And Greenland is melting faster than at any point in recorded human history. The GRACE and GRACE-FO satellites have measured the loss continuously for over 2 decades, and the trend is accelerating, not slowing. Every year, the freshwater driver behind that 53-kilometer drift grows stronger. Here's the fact that turns this from a model result into something far more serious. It has happened before, and the planet kept the record. About 12,800 years ago, near the end of the last ice age, a massive pulse of fresh water from a melting North American glacial lake drained into the North Atlantic. The conveyor slowed dramatically or stopped, and the climate of the northern hemisphere snapped back toward glacial conditions within decades, not centuries. The numbers are stark. Greenland cooled by about 10 degrees Celsius. Europe cooled by 2 to 6 degrees. Sea ice spread south across the North Atlantic. The episode, known as the Younger Dryas, lasted about 1,300 years before the conveyor recovered. And the trigger was fresh water. The same kind of fresh water Greenland is delivering into the same patch of ocean right now. We know this from ice cores, lake sediments, and ocean records across the entire hemisphere, all recording the same abrupt cooling. That is what the Younger Dryas adds to the Utrecht finding. The mechanism the new model describes, fresh water choking off the sinking and stopping the conveyor, is not a theoretical scenario built inside a computer. It is a thing that physically happened to this exact ocean. The collapse the model warns about has a real precedent, with consequences written into the geological record. And the new study is not the only modern evidence pointing the same way. The Utrecht result is the latest entry in a body of evidence that has been building for years, and every major piece points in the same direction. In 2021, a reconstruction led by Levke Caesar, published in Nature Geoscience, found the conveyor weaker than at any point in roughly the past 1,600 years. That places the current state completely outside the range of natural variability across the entire span of recorded civilization. Whatever is happening now is not the normal cycle. That same year, Nicholas Boers published a study in Nature Climate Change, applying 8 independent statistical early warning indices to the conveyor's record. Every one of the 8 showed the same thing: loss of dynamical stability, the fingerprint of a system approaching a tipping point, Boers called the trajectory worrying as well as surprising. Then, in April of 2026, a study in Science Advances tightened the picture further, using real salinity observations to constrain climate models and producing a roughly 51% slowdown estimate by the year 2100, well above the previous consensus of about 32%. And Stefan Rahmstorf, who has studied this current for about 35 years at the Potsdam Institute, recently moved his own estimate of the probability of full collapse from roughly 5% to greater than 50%, calling it the most dramatic climate change in 100,000 years. Look at the strength of that combined picture. The unprecedented 1,600-year weakening, documented. The loss of stability, confirmed 8 separate ways. The projected slowdown, sharpened and worsened. The leading experts' collapse probability crossing 50%. When that many independent lines of evidence using different methods and different data all arrive at the same conclusion, the case no longer depends on any single study being perfect. The convergence itself is the evidence, and the convergence points one way. Now, this topic attracts a few claims online worth dispatching quickly. The idea that this is just a natural cycle is contradicted by Caesar's 1,600-year record, which captures the full range of natural variability and places the present state outside it. The idea that it is just noise from one sensor array is contradicted by the 2 independent data streams behind the 53-kilometer drift, which have nothing to do with that array. And the idea that geoengineering is responsible collapses against the energy budget. Nothing humans have built can push a 1 petawatt conveyor 50 times the power of all human civilization. And the real driver, Greenland meltwater diluting a density contrast, is measured and well understood. The anxiety behind those claims is reasonable because the situation is genuinely alarming. The explanations are not. What the new study adds to all of this is the one thing the others lacked: a mechanism in a real-time observable that confirms the collapse is already underway. For the first time, monitoring this current is a forward-looking job rather than a backward-looking one. The field no longer has to wait and reconstruct a collapse after it happens. It has a satellite observable signal that updates continuously. And the single most important thing to watch is the drift rate. Stage 1 is slow, steady drift. The moment that drift begins to accelerate is the moment the system starts crossing toward stage 2. Researchers will also be watching Greenland because the faster it melts, the faster the freshwater forcing accumulates, and the faster the conveyor responds. Continued acceleration would compress the timeline. A slowdown would stretch it out. It is important to be clear about what this study does and does not say. The 400-year stage 1 figure is model output under idealized forcing. It is not a countdown, and anyone presenting it as a date is misreading it. What the study delivers is a mechanism, an observable and confirmation that the predicted signal is already in the real data. That is enough to take seriously without inventing a deadline the evidence cannot support. But the stakes, if stage 2 arrives, are not abstract. European winters would drop about 10 degrees Celsius. Northern European agriculture, built around mild winters for centuries, would fail at scale. The tropical rain belts would shift, weakening the monsoons that feed over 1 billion people in West Africa and South Asia. The collapse of nutrient upwelling would starve the base of the marine food web. Sea level along the United States east coast would rise an additional 50 to 100 centimeters. And roughly half of model runs show the conveyor does not recover even after the freshwater stops, meaning a collapse could be effectively permanent on any timescale that matters to us. So here is where it stands. For 20 years, the field could only watch the conveyor slow down. Now it can read the gauge, and the gauge says we are already in stage 1, with about 53 kilometers of drift on the record. The needle is off 0. The one thing we cannot yet see is how fast it is about to fall. We will be tracking that drift rate closely, because it is the number that will tell us whether the most important current on the planet has decades left or less. And we will let you know the moment it moves.